All right, so this section is titled Angles and Their Measures. Okay, so like I said, we're going to kind of look at angles in a little bit of a different way. So I'm going to kind of start just by thinking about things sitting on a coordinate plane for a moment. Okay, so if we put an angle on the coordinate plane, so let's say we've got one ray heading off this way and another ray heading off that way, then that's going to form an angle. Okay? And we're going to use a little bit of a different variable. You've maybe seen this before, maybe not. Anybody recognize what that is? It kind of looks like a little egg with a line through the middle of it. It's called theta.
Oh, I was right.
Yeah, you get. And theta is kind of the variable we use to describe angular stuff. So if you see the variable theta, probably something with angles is going on. Okay? So in this angle here, this ray that's sitting on the x-axis would be called the initial side. And this other one here would be called the terminal side. So what does the word terminal mean? An ending, right? If you're at the airport and you're going down the terminal, it's called a terminal because that's where the planes meet up with you at the end, right? When something terminates, it's done. Like the Terminator movies, right? They kill you and you're done. Anyway, so initial side, that's where it starts. Terminal side, that's where it ends, okay? And we want to think of this as more of like, kind of envision the initial side kind of staying put, and then this terminal side has kind of a rotational movement to it, okay? So we can kind of keep pulling that ray around, and however far we rotate it, whatever that angle of rotation is, that would be the angle measure then, okay? So we're kind of coming from a place like that, okay? And we'll get into more of this actually a couple sections down the road. We'll dig into this a little bit deeper, but I just want you kind of thinking about that idea of a rotation then as an angle measure like that, okay? So the first thing, though, I want to talk about specific to this section, though, is degrees versus radians. And you guys are probably a little bit more used to degrees than radians. So I'm going to start there. Does anybody know why we have 360 degrees in a circle? Yeah. It's highly divisible. That's basically it. Okay? So back in the day, someone was looking at this situation of, well, I want to be able to easily describe a circle, and so that if I were to break it into chunks, that things would just stay nice and neat. I wouldn't have to worry about fractions or decimals or any of that kind of stuff. And so they took a circle and they kept dividing it up and dividing it up and dividing it up. And the number 360 degrees is highly divisible. So I can break up my circle in lots of different ways and still end up with whole numbers every time. Okay? So right now I've actually broken it up into 45 degree chunks. I could do it that way. Still going to be 360. Each one is 45. You could chop it into little 30-degree angle pieces, and they'd all sit in there real nice. You could chop it up into 10-degree little pieces, and that would all sit in there really nice. And so like it all just kind of fits nice. Okay, but other than that fact, the number 360 is pretty arbitrary, though. Okay, 1 degree doesn't hold any kind of special meaning. Radians, however, a radian does. So does anybody remember how many radians there are in a full circle? 2 pi. Okay. Now 2 pi, just by its very nature, it's an irrational number, right? It goes on forever, decimal, decimal, decimal. It's not highly divisible at all. So why in the world would I want to use radians? What's making that a convenient thing? Okay, well, The radian comes from the word radius. Okay, it has a relationship with the radius of the circle. So let's say the radius of my circle, sorry, that's kind of hard to read. Let's say the radius of my circle is 1 unit. Okay? So what is the circumference of the circle? You guys remember the formula for circumference of a circle? 2 pi r. So if the radius is 1 unit, what's the circumference? 2 pi times 1, which is 2 pi. Notice anything? What? The circumference and the radian measurement all the way around are the same. Okay? That's where a radian came from. Okay? And so the definition of a radian then is, since it takes 2 pi radians to go all the way around, and there are 2 pi units all the way around, okay, 1 radian would be probably somewhere kind of like this. This would be about 1 radian. And the idea is that then the length of the arc that far, if it's 1 radian, would be a circumference, or it would be an arc length of 1. Okay? So with a 1 unit radius circle, whatever the angle is that you open up in radians, the length of the arc is the same. It's the same length. Okay? So I'll come down here and kind of clarify a little bit. So a radian is let's see, it would be a good way to say this. So a central angle so the central angle of 1 radian has an arc cut at the same length if the radius is 1 unit. So it became kind of the standard unit of measure that every time, if I start with a circle that has a radius of 1 unit, like I said, every time I open it up a certain number of radians, the length of the arc that's being cut out is also that. So 1 radian has an arc cut that is also 1 unit. Okay, so maybe under same length, we could just say 1 unit to kind of clarify that. Okay, if that radius was 1 unit to start with. Okay, so by the time you open it up all the way around the circle, the arc length has become the entire circumference then. And so since we know the circumference is 2 pi, the radian measure for that should be 2 pi as well. So the real kind of meat and potatoes of this, what we're going to do with this is, can we easily convert between degrees and radians, because both of them are used pretty frequently. Okay, and so we have a way to convert because we know a whole circle is both of those two things, right? Which allows us to make a ratio. Okay, there are 2 pi radians in every 360 degrees. Okay, so you can make a little fraction out of that we can then multiply with to help us convert from one to the other. Okay, now you don't usually use 2 pi over 360. Typically, it's pi over 180. Okay, so how can I get to that from what I have here? Yeah, right. You just reduce the fraction, right? Divide everything by 2. So Yeah, so this is kind of more the accepted conversion. There are pi radians in every 180 degrees. So you might want to use this one. But I could have just as easily made this fraction the other way. So we also have 180 degrees in every pi radians. And it kind of just depends on how you want to convert as to which one of these two fractions you're going to use. Okay, so give you an example. Let's say I want to write 60 degrees in radians. Okay, so I want to multiply by something where, or some kind of conversion where the degrees are going to cancel and I'm going to be left with radians when I'm done. So which of these two do I want? First one or second one? Yeah. Nope. First one. I want to cancel the degrees. So whatever's on the bottom of that fraction should be what I have, and I can cancel that, and then whatever's on top is what I'm left with. So if I take 60 degrees, multiply it by pi radians, and if you don't want to have to write the word degrees, that's fine. You can just do 180 degrees like that, and that'll work. Okay, so this is going to become 60 pi over 180. If I take that 60 and multiply it with that pi, and that's going to be, now the degrees have canceled, now I'm in radians. But I can simplify that fraction up quite a bit, right? 60 over 180, what does that reduce to? Yeah, so it would be the 60 and the 180 would cancel down to a 1 over 3, so this would then become just simply pi over 3. And we're going to do a lot with fractions with radians because of this kind of thing. It ends up happening quite a bit where your radians are fractions involving pi then because of this. Okay. Something else that's probably important to mention, radians, you don't have to always write the word radian if you don't want to when you're doing these. Radians are technically a unitless measurement because it's of an angle. Okay. So if you want to keep writing the word radian, you can, but you won't always see me do that. And one thing that I'll just kind of mention here is if you have a number and you're not sure if it is in degrees or if it's in radians, you simply need to look for one thing. Does it have the little circle? Does it have the little degree symbol? If you see the degree symbol, it's in degrees. If you don't, even if the number looks more like a degree number than not, it's technically in radians then. Okay, and we'll do a few like that just to keep you guys honest. Yeah? Oh, the unit circle? Yeah. It's like next week, week after. It's coming up, but we will. We will. Okay, so let's do another one of these. Let's go the other way. Okay, so let's say I want to convert 3 pi over 5 to degrees then. So this time, I want to go with the second one, right? I want to cancel radians and be left with degrees. So 3 pi over 5 multiplied by 180 over pi. And so let's take a look and see what happens there. So first of all, what do you notice? What's something that's going to cancel? Pi's will be gone, okay? So then we'll have 3 times 180 over 5. Okay, and maybe you want to cancel the 5 with the 180 first, or you could do the 3 times 180 and then divide by 5. Doesn't matter. Either way, we should be ending up in the same place here, so. So I'm getting 108. Double check me on that, but looking like 108 degrees should be our 3 pi over 5. Okay, so you guys have done this before, right? Yeah. Just converting back and forth stuff? Okay. Have we ever seen DMS before? Did that sound familiar, or is that one a little foggy? This it doesn't normally gets used. It gets used primarily just with like nautical stuff. So people that are like out on the sea and like they want to change the angle of how far they're going or whatever, you'll see this. And like in aeronautics too, like you're flying a plane, that sort of thing too. So let's talk a little bit about that. So DMS stands for degrees, minutes, seconds. Apparently there were some people out there that were sailing ships that really didn't like decimals for some reason, so they had to come up with this. And it's kind of confusing because it uses the words minutes and seconds, and people think minutes and seconds, and what do you automatically think about? Time. And this is not time. Okay? However, things are broken up the same way that minutes and seconds are, though. Okay? So, there are, in 1 degree, there are 60 minutes. Just like in 1 hour, there are 60 minutes. Okay, but now degree is kind of the starting point. And just like with time, in 1 minute, there are 60 seconds. So if I'm given some kind of a degree measurement that is a decimal, okay, we might want to then convert it into, okay, well, how many minutes and seconds is it, rather than just the decimal? Or if I know how many minutes and seconds I have, then how do I work back and figure out what is just the decimal for the degree? Okay? So let's try that once. So let's say I've got 30.65 degrees, and I want to convert this to DMS. Okay, so the 30, I don't have to do anything with that, okay, because I have 30 degrees and then some extra, right? And my 30 degrees are still going to be 30 degrees. It's only that 0.65 that I'm really concerned about into turning into minutes and seconds then. So I can hold on to the 30 degrees. And so then I want to know, okay, so 0.65, what happens to that going into minutes and seconds? So how do you suppose I could do that then? If there are 60 minutes in a degree, 60 seconds in a minute, what can I do with that 0.65 to get myself started? Yeah? Okay. So I've got 0.65 degrees, and you said multiply it by 60. And the reason we're going to do that is because there are 60 minutes in 1 degree. Do you see how we're doing the same kind of like dimensional analysis type thing? We're going to cancel units and all of that. Okay. So I'm going to cancel out degrees here, then I'm going to end up with minutes when I'm done. So 0.65 times 60, what's that get us? 39? Okay. And so then how many seconds are there? None, right? Because I got 39 whole minutes. There are 60 seconds in a minute. That's great, but I don't need to worry about that because I have 39 whole minutes, nothing left of any little pieces. So my answer for this one would be 30 degrees, and then we use a little 1 tick mark for minutes, and then 2 for seconds. So it'd be 30 degrees, 39 minutes, 0 seconds, like that. Mm-hmm.
Do you even have to put this 0 seconds?
Usually it's there, but technically no, you don't. Okay. Now, let's say that this didn't come out to a whole number, this 39. Then what would I have to do to find seconds? Just do the decimal again. Just strip off the decimal, multiply it by 60, do it again. Mm-hmm. And sometimes you might end up with seconds that are decimals, and then you just leave it as a decimal because we don't break it down any further than that. Okay, there's not like nanoseconds or something in this. It's done. Now, might want to go the other way though. What if I got something that's already in DMS and I want to move it back into just some kind of a decimal for degrees? So then instead of multiplying by the 60, you're going to start dividing by 60. Yep. So let's say I've got 72 degrees, 15 minutes, and 20 seconds, and I want to convert that back into just degrees. Okay, now we could do this process of, divide by 60, and that works. That's fine. The way I like to do it, and you can do it the other way if you want to, but the way I like to do it is I say, all right, I got 72 degrees plus I've got 15 minutes. If I have 15 minutes, that means I have 15 sixtieths of a degree, right? And if I have 20 seconds, I have 20 3,600ths of a degree, right? Technically, that's 60 times 60, which is 3,600. So if I take these little fractions and add those together and then tack that on the end of 72, that should be my decimal then, right? So this always works. If you just do the minutes over 60 and the seconds over 3,600, add it all up, boom, done. Or you could take 20 divided by 60. That's how many minutes you have. Add that to 15. That number over 60. That's how many degrees you have. Add that to 72. Done. Okay? But I think for your money, this works a little faster. Just got to be careful of how you type in your fractions when you do it, but it is effective. So 20 over 600. All right, so I got, and this is a bit of a repeating decimal, so I'm going to just do this, 72.25, and that's repeating degrees. That's what we have for this one. And if you want to round these, I'm okay with that too. Just at least a couple of decimal places. I'd say maybe 3 to be safe, but it should be fine. Okay, so that's the idea with DMS. Are we okay going both ways with those? Okay, all right. Okay, the other thing we were talking about was, like back at the beginning, was this whole arc length idea, and I want to get back to that a little bit because that's going to help us answer some story problems involving rotations and that sort of thing. So, come on. I'm going to write down the formula, but then I'll talk a little bit about why it is what it is. So we use the letter S for arc length. I don't know why. Just do. So, and it's a pretty simple formula. It's just R times theta. Okay, so the S is the arc length, so some kind of, in inches or feet or whatever. R is the radius of the circle it's on. So we'll just say like radius of the circle the arc is from, because every arc is like a little piece of a circle. And then the theta is the angle, but the key here is it must be in radians. So if you want to find an arc length and you're given an angle that's in degrees, you're going to have to convert it into radians first. Okay, now think about this for a second. If I have a whole circle, we talked about this with radians. Let's say its radius is, for the sake of argument, 3. What would be the circumference of this circle? Use your circumference formula. It's 6 pi. And how did you get that 6 pi? Is that not just an arc length? Isn't a circumference just an arc length? It just happens to be the whole circle. What's the radius of that circle? 3. What is the angle of that arc? It's 2 pi, or 360 degrees, but 2 pi, right? So take a look at how we calculated this. Isn't this just the same as this? Right? Radius times the angle in radians, 3 times 2 pi. When you do a circumference, you're doing an arc length. That's all it is. Okay? So this little idea, though, just continues to work no matter what the radius, and even if that angle happens to be less than 2 pi, you could plug in some other kind of an angle measurement, and it would still get that little piece of the circle, not just the whole thing. Okay? This is actually where your circumference formula came from. This came first. This formula, you were just never told that. This came first, and then this circumference formula came from that. That's why there's a 2 pi in there all the time for circumference, because the angle is always 2 pi when you do a circumference. So let's try this out a little bit, make you do a little conversion on this one. What is the arc length of an arc cut at, let's say, a 120 degree angle from a circle with a 2-inch radius? All right, so what's the first thing I'm going to have to do with this one before I can start actually getting the angle? I got to convert to radians, then I can get the arc length. So I take 120, and this is in degrees, so what fraction am I going to multiply it by? Pi over 180, yep. And 120 and 180, we can reduce that maybe before we even put this thing together. What is 120 over 180? Be, yeah, 2/3. Yep, you're right. So this would be then 2 pi over 3, right? Because 120 over 180 makes it 2/3. Yep. Okay, and so now I'm ready to multiply. So my arc length is the radius, which is 2, and my angle, which is 2 pi over 3. So I end up with 4 pi over 3. And what should be my units for this? 2 pi or 4 pi over 3 what? Inches. And think about this, the dimensional analysis on this thing too. 2, what's the unit for the 2? Inches. 2 pi over 3? Radians. But remember I said radians are unitless. So what's inches times something with no unit? Inches, right? So 4 pi over 3 inches. And that makes sense because we're talking about the length of an arc. It should be in some kind of inches, feet, whatever. So, yeah. So it happens to not be such a nice, neat number, but that's it, 4 pi over 3. It, like when you do problems like this, when you're multiplying things together, the radian part of it never carries a unit that affects the answer then. So it doesn't, so it's not like 4 pi over 3 inches radians. It's just inches. It doesn't have any unit that applies to it there. So, okay, so now that we're doing some arc length stuff, let's take a look at doing a story problem involving some rotational stuff and see if we can pull this all together. And this will be the last thing that we do actually today. And then I'll let you guys get some work in.
How long is this going to be?
How long is what? This example? Maybe like a third of the page or something. All right, so we're gonna talk about a wheel rolling down a hill. So it is rotating at a speed of 5 rotations per second. So pretty fast. So the wheel has a 26-inch diameter. So how fast is the wheel making contact with the street? Okay, so I'm talking like inches per second. How fast is it going down the street? Okay, we have a speed that's a rotational speed, 5 rotations per second, but I want to know if I were to like actually clock it moving down the street, you know, from one point to another, how fast is it actually traveling down that road then? Okay, so we have to take this rotational speed and kind of like convert it somehow into this like linear speed going down the road. Okay, so first thing that we want to do then to kind of connect those two things is if I have a wheel that has a 26-inch diameter, what is its circumference? Because that's going to be important because that's the part of the wheel that actually makes contact with the road, right? The circumference of that wheel. Okay, so 2 pi r, so 2 pi, what's the radius? 13. Good. Careful with that because I gave you a diameter there. We could do that too. Yeah, you guys are used to 2 pi r, so that's why I wrote it that way. But technically, pi d is another way to do circumference, right? So, but either way, we've got 26 pi. Oh, and what's the unit for this then? Inches. It's the circumference, right? So it should be in inches now. Okay, and we want to somehow, like I said, get from rotations per second into inches per second. So I've got 5 rotations every 1 second. But a circumference, doesn't that give me how far down the road the tire's going to go in 1 rotation? Think about that. As the circumference, as the wheel makes contact with the road in 1 rotation, that circumference is going to touch the road exactly all the way around the wheel, right? So in 1 rotation, how far does the wheel go down the road? 26 pi, right? 26 pi inches is how far that wheel will go in 1 rotation. So 26 pi inches in 1 rotation. Okay, and see how I'm using rotations as a way to kind of get the units to work out the way I want? Okay, 5 rotations per second, 26 inches per rotation. I can cancel rotations and I'll end up with inches per second there then. So 26 pi times 5, and you can go ahead and drop the pi and just leave it as a decimal because that's going to make a little bit more sense for what we're doing here. But 5 times 26 pi getting about 408.41. So that'd be inches, yeah, that many inches per second, right? So that wheel is traveling 408 inches per second down the street. Okay. So, yeah, so let's do a little bit more converting here. Is 408 inches per second fast or not? No. Well, let's put it in miles per hour and we'll see. Because that's something we're a little more familiar with. I don't know exactly. Yeah, it's just like, yeah, it's somebody was in like a garage or something, and oh crap, there goes the wheel, and it's down the road. So. Let's say it's really slippery and its coefficient of friction is like way up there. So, okay. Anyway, so what do we need to multiply by to get this thing into miles per hour? Then some people give me some things we should be throwing in here. Do what now? Multiply or divide? So 60 seconds in 1 minute. All right, that's good. So that'll get rid of seconds, right, and leave minutes. And then another 60 minutes in 1 hour. So that's going to take care of the time. So now we're into inches per hour, but I want to be miles per hour. So what else should I be doing here? So we're doing inches. So in 1 foot, we got 12 inches. So now I'm up to feet per second. No, feet per hour. And then divide by what? There you go. Because there are 5,280 feet in 1 mile. All right, so feet cancels feet, inches cancels inches, seconds cancels seconds, minutes, and I've got miles per hour. So let's see what we get here. So, is it fast or not? So, yeah, 23 miles per hour. It's making a decent clip down the road. Yeah, probably. So, ask Mordike about terminal velocity. I don't know. But I think 23 miles per hour, if it's a really steep hill and that wheel really gets going, is totally legit. So I'm going to stick with that. All right, anyway, so that's using that, bless you, that's using that rotation idea with the circumference to take a rotational speed and turn it into a linear speed. That's kind of the trick with this. And then from there, they might have you doing some other kind of conversion type stuff as well. Okay, so, all right, I'm going to let you guys get started on your homework then.